right. Welcome, everyone. Thank you for being here. So I'm really pleased that we have Maxime Popoff here from INSA Lyon to give this seminar. For a bit of context, I had the pleasure of reading and discussing Maxime's thesis as an examiner last year, and I think it's just really fascinating work that he's doing, building really high-performance audio systems with FPGAs. So we're talking about an approach which combines some cutting-edge technology in terms of audio channel count, audio latency, efficiency, with a really nice tool chain and workflow to be able to work from high-level programming languages like Faust. And I think in this talk he'll sort of demonstrate how that works, and maybe we'll be able to see some little examples of it. So, Maxime, happy to have you here.
Yeah. Thank you, Andrew, and thank you everyone for coming. So my name is Maxime Popoff, and today I will present you my work, the work that I did in my thesis, and the work of my research team under the project Polyphonic, which enable massively scalable and ultra-low latency audio system with FPGAs. First, a little presentation. So I'm a researcher in computer science. I have a PhD from INSA Lyon, and my thesis was on the compilation of real-time audio DSP on FPGA. So my research focused on embedded audio platform and their programming, and I work within the Emerald team. So it's a research team in Lyon that gathered a team from INRIA, which is a French research center, INSA Lyon, which is an engineering school, and Gram, which is the birthplace of the Faust programming language, if you know what Faust is. And so I'm the founder of Polyphonic. So basically, after my thesis that I defended in December last year, I was granted a fund to start a company with the technology I developed during my thesis. So the name of this company is Polyphonic. For now, it's just a project. It's not an official company. And so, yeah, I'm found during 1 year under the name of Polyphonic. So just to be clear, Polyphonic is born from the Cifala project, which is the research project that we did with my research team, the Emerald team. So the objective of Polyphonic is to unlock high performance, low latency multi-channel audio processing with FPGA. So the idea is to make FPGA easier to use for audio. It's held with two main components. First, a dedicated compilation flow, a dedicated software that streamlines the development. So you can basically program FPGA using high-level language, such as Faust, which is an audio domain-specific language, or C++. And you have a physical board that allows you to interface with existing audio system. What I mean by that is, if you program your FPGA, you still have to find a way to connect many channels, to have DAC and ADC, to have everything working well with low latency and with high channel capabilities. So this board is developed and allows you to just program an FPGA and having everything working with an existing system. What I mean by that is just with some speaker and microphone, you can just directly plug it and it's working. So again, the objective is to enable the creation of audio system with hundreds of channels and very, very low latency. We are talking about 10 microseconds, 15 microseconds from analog input to analog output, without having to know how an FPGA works, or without having to know deeply how an FPGA works. And so we want to bridge the gap between artistic creation, creative application, and raw computing that can afford an FPGA. So for this presentation, I will stay mostly high level in my presentation. I will try to explain very quickly what is an FPGA. So if you have no idea what I talk about for 5 minutes, at least I hope you will understand what an FPGA is. We'll see why it's pretty hard to use in the context of audio application. I do a small introduction to the Faust programming language. And then we will see the more complex applications. So we will see how the Cifala toolchain works, so the software part. And I will present some board I developed to help audio integration. Let's start with some context, and we'll see what is an FPGA basically. So just very, very high level context. What is real-time audio DSP? So this is just 3 basic examples. Hearing aids, noise cancelling, headphone, or guitar effects. We are talking here real-time audio DSP. So let's say you want to make your own device that can do real-time audio DSP. What are your solutions? What can you program to do real-time audio DSP? You have many solutions. So first you can use an embedded CPU. So I suppose most of you know Bella. So the 2 main ones for low latency are Bella or Elk Audio, even if I'm not really sure Elk Audio is still very used. They are based on a Linux Xenomai, which is a very, very low latency OS. And you can have sub-millisecond latency so in this case, you have an embedded CPU, so you have to deal with an OS. Maybe you want something more lightweight. So you can use a microcontroller. The main one are probably the TNZ or ESP32. There is many other ones. It's suitable for sub-millisecond latency latency see application. There is some example, but there is a very limited computational power at this latency latency. There is some, it's very new, but there is some promising approach with GPU. In recent paper, there is an application with a 96 speaker application achieving sub-millisecond latency. It's still very experimental. If you want to use it without really knowing how a GPU works, I'm not sure it would be very easy. But yeah, GPU are very promising on this field. And finally, there is FPGA. So they are highly adapted to audio DSP, and they have a very high potential for parallelization. So first, you can do sample per sample computation, which means you don't buffer anything. So as soon as the samples come in, you process it and you output the sample. So you don't have any latency of any buffer. You can use very high sampling rates, more than 20 megahertz. That's also participate to the low latency. And you have a very, very high number of GPIO. So the GPIO, basically, they are the physical pin on your chip. And the more GPIO you have, the more channel you can connect to your chip. And we are talking hundreds of GPIO in one chip, where on a microcontroller it's more like, I don't know, maybe 30, 40. So FPGA are already used in commercially available products. You have here just 4 examples, there is more. So in the Innovation Summit keyboard, they are used to implement very high sampling rate oscillator. In the antelope audio interface, they are used for their computational power. Here you have the holoplot speaker matrix. So each square is 96 speaker. This is what equipped the Las Vegas Sphere, the new concert venue, if you see it. And here it's used in a digital mixer for their parallelization capabilities. So they are used in commercially available products, but not so much. Why? Because it seems to be very, very nice. Because basically they are extremely hard to use and to program. So unless you are a hardware engineer, it's going to be very hard for you to use them, which is the main problem for FPGA. So to understand why it's so hard to use them, I will briefly explain what is an FPGA. So yeah, this little square here is an FPGA. So to be exact, this one is a system on chip, which means that under this silicon you have an FPGA and a CPU and some memory, some buses, some interfaces. So an FPGA is an integrated circuit that is, so we can say programmed, but usually we say configured using hardware description language, such as VHDL or Verilog. What is very, very important here is that it's reconfigurable hardware. It's not software. So inside an FPGA, the basic block is CLB, so a configurable logic block, which is made of a lookup table and a flip-flop register. So the lookup table allows you to do any logic function, and the flip-flop will sequentialize everything. So you have billions of CLB in an FPGA. Then you have some embedded memory called block RAM. You will have some hardware mathematical function called DSP block, nothing to do with audio DSP. And you can interconnect everything with a reconfigurable interconnect. You have a lot of I/O, and by configuring everything, you can have any logic function that you want. What is important here is that you have those 4 resources. So we mostly never talk about configurable logic block, but we talk about LUT and flip-flop. And you have the BRAM and you have the DSP. So those 4 resources are the main importance when you program an FPGA. Because it's reconfigurable hardware, if you don't have enough resources, you cannot run your program. On a CPU, if you have a very, very heavy program, it will just take a long time to execute. On an FPGA, it will just not fit and you cannot execute it. So you need to have a program that uses less resources that you have. So yeah, limited resource, very, very important. Usually, we program an FPGA using hardware description language, again, VHDL, Verilog. I won't go into the detail. It describes the structure and behavior of the circuits. The idea is that you have to know, to have some background in microelectronics and to know how hardware works. So it's not just some hard language to use. It's really you have to know what happened at the microelectronic level. So for many, many years now, we have something called high-level synthesis, which is a tool that allows you to program an FPGA using software-based languages such as C++. The main one, it's System C, I think there's one. So you can program an FPGA using C++, which is very nice. You may thought it's not. The problem is you still need to know the hardware part. You still need to have a background in microelectronics. You still need to write your C++ code in a very specific way in order to have an optimized implementation. I will show you a very simple example here. We have, yeah, you can read it. We have this very small function, which is basically an FIR filter. So it's a multiply and accumulate function. You just 10 times you do I times I, and you accumulate everything in the out variable. So it's C code, C++ code, and you can give this to the high-level synthesis tool, and it will be implemented on your FPGA. The question is, how? Will it use one multiplier, one adder, and just reuse the same circuit 10 times, which will save a lot of resources but use a lot of latency? Or will it parallelize everything, use 10 multiplier and adder 3, so 6 adder in this case? It will be very, very fast to execute, but use a lot of resources. There is none of those approaches better than the other one. The question is just which one is it and which one do you want to implement? So you need to add something else in your code to guide the tool or to impose one of those approaches to the tool. And also you have all the in-between approach, maybe half parallelize or anything. So first you need to understand which one is better for you, which is not something that you do usually with software programming. And that's not all. So here I just explained to you how you program the FPGA part, but if you remember, we have a CPU, an FPGA, we have some memory, we have a whole system. So you need to program the whole system. You need to interface the CPU and the FPGA. You need to interface the external memory with probably a DMA. You need to, very important, balance the computation between the CPU and the FPGA. I just come back to this later. You need to interface the FPGA with the external audio signals, so with ADC and DAC. You need to deal with clock issue that you will have, and most of the time you use fixed points in HDL. And again, hardware circuits, so you need to know how hardware work. So you need to know a lot of stuff that you don't especially want to learn just to implement your audio DSP on FPGA. This is where we are going. So the idea is to simplify FPGA development. So we want you to just program something in Faust or in C++ and just ignore all the other parts. And you put this in our compiler, and you have a working FPGA code. Doing this, we want to keep the latency as low as possible to achieve sub-millisecond latency processing. We want to have something scalable that, depending of your DSP or the number of input and output you want, we adapt the design of the FPGA. And we want to optimize the design that is implemented on the FPGA, because when you do hardware, there is, again, many, many ways of implementing the same code. We want to be sure that the one you implement is efficient. Maybe not the most efficient, but at least it's efficient. So yeah, this is the objective of my project, of the research we do at Emode. And now we'll see how we do that with the compiler exactly. So the compiler, the whole software is called Cifala, which was also the name of the research project. So the idea of Cifala, again, we want to use high-level language to program an FPGA. And we will use the Faust programming language. So what is Faust? It's a functional programming language for real-time audio signal processing. It has been developed for many years now by the member of Emode team, so by the member of Graham in Lyon, and they are now in the Emode team. So the main strength of Faust is that you can target many languages. So you program in Faust and you ask the compiler to transpile it into another language. And it's very, very efficient. Sometimes the implementation is more efficient than if you write it by hand in the other language. And you have a very high level of control on the generated code. So it's especially the case when you have the member of the Faust development team in your team. But yeah, you can have control on the generated code. And you have many, many, many libraries that are developed around the world, especially by people at Karma in Stanford. I think Julius or Smith did a lot of work. And yeah, it's open source, and you have an online IDE. I will show you that just now. So basically, if you want to try some Faust code, you can go to this URL if you see it. So you just write Faust IDE on Google, and you can write your code. So everything is running on the server. I won't explain this program here. It's just a simple program that we use as a Hello World program. And just so you know, in Faust program, the process line is like the main. It shows what your signal will go through. I can have the diagram here that is automatically generated. And yeah, we call a function here that generates a sine wave at, you don't see anything, you don't see much, it's maybe better. At 440 hertz, and it goes through some multiplier, kill switch, anything. And here we define some sliders, some user control. I can make you hear the noise. So again, it's just a Hello World program, and you have some control over it. It's a virtual analog simulation. So the idea is just to have a sound that we can manipulate. So this is Faust. And so yeah, let's say you are working on this online IDE, you are making your DSP, and now you want to implement it on your FPGA. How do you do that exactly? So let's go back to the presentation. The first thing, so you could think that I have my Faust program. Faust can transpile to C++. So I just generate a C++ from the Faust. I give this to the high-level synthesis that takes C++ as an input, and I have a working FPGA implementation. First, no, because you don't implement any interface with external ADC, DAC. You don't have any driver, anything. But let's say you implement that too. It may work, but you will be very, very inefficient. If you remember well, we have a very limited number of resources on our FPGA, and if you just implement everything on the FPGA, every function, every computation, you will saturate the FPGA resources very, very quick, and you don't want to do that. So you want to offload computation on the CPU as much as possible. You want to do only critical operation on the FPGA. The problem is, how do you know which operation can be done on the CPU? Because if you have a very critical computation, how can you be sure that some computation can be done on the CPU without affecting the critical operation of the FPGA? It's done with something called control rates. So historically, if you implement a DSP on a CPU, you will use a buffer, let's say a 32 samples buffer. The control rate is updated only once for every buffer. So the control rate usually depends on some user input, some knob, some slider. The idea is that if you handle 32 samples in one buffer, you just read once the controller for the whole buffer. So you update the control 32 times slower than the sample rate. 32 times, 64 times anyway, but just it depends on the buffer size. But so the control rate is way slower than the sample rate. So we can do every critical computation, every sample rate computation on the FPGA, and the less critical computation are done on the CPU, on the ARM. You have the same thing from the memory. Basically, FPGA embeds some VRAM, as I told you before. This memory is very small. So if you put everything on this small memory, you will saturate everything very quickly. So you want to put large array on the DDR, which is slower to access. What I mean by large array is like delay line. Basically, if you implement a delay, you will have lots of samples that you need to put on the DDR. But that's OK, because for a delay line, you will only save a sample and read a sample once every sample. A delay is just one sample that you read somewhere in the memory. And we can do few external DDR access per sample. We have time for that. We just cannot store like 1,000 of coefficient on the DDR. We don't have time to read 1,000 coefficient every sample. So we want to do this dispatching, which is very, very important to have an efficient implementation. How do we do that? So this is another Faust program example. I will explain a little bit what happened here. So again, the important line is the last one, the process. So we call a sine OSC function that goes through an echo, that goes through a multiplier. The sine OSC function is declared here, in line 3. It's called a Faust function, that is os.oscrs. It's a sinusoidal oscillator based on a resonant filter. We just want to generate a sine wave here. We don't use a wavetable because it's a good example of how you need to think your program on FPGA. A wavetable is a lot of memory access, and you cannot do that much. So we prefer to have the mathematical approach to generate the sine wave, which is way more adapted to an FPGA. The problem is, to have a sinusoidal oscillator, we need to compute the coefficient of this filter inside this function, which rely on the sine and cosine function. If you try to implement a sine and cosine function on an FPGA, you will have very few room for other stuff. Those functions are huge. You don't want to implement the sine and cosine function on the FPGA, but we'll see that later. And finally, the echo is here just to add lots of memory needs to our program. So how do we implement this on our system? Well, the sinusoidal oscillator generates the sample, so it's very critical. We implement it on the FPGA. But the coefficient, the value of the coefficient, don't need to be updated at every sample because it depends on f, that you can see here, sorry. And f, yeah, is declared here as a slider, so as a human control slider. So you don't need to to refresh the value of the coefficient of the filter at every sample, you need to refresh them only when a control is changed. So it's not critical at all. You can do everything on the CPU, which means you can do the sine and the cosine on the CPU. So you just free a lot of resources on the FPGA right now. The echo will affect the samples, so we need to implement it on the FPGA, but we store the echo samples on the DDR. Again, because an echo is just one access every sample, so it's very, very quick. And yeah, here we are, the computation and the FPGA CPU dispatching. Just doing this, you save a lot of resources on your FPGA, and you will be able to implement more complex DSP. So yeah, it's great. We know how to dispatch everything, but how do we automatize everything? How do we do that not knowing what audio DSP you are programming with this? So sorry, usually I just make this appear step by step. Just focus on the top of this schema. The Faust compiler do everything, basically. The Faust knows if a computation is at the sample rate or the control rate. Because on a typical CPU implementation, you already need this information and you use it. So we have this information. So we just change a little bit the Faust compiler, and we ask it to generate different files. One only contain the control rate function computation, and one only contain the sample rate computation. And again, the Faust compiler already know this information, so it can split everything. So if we just take those two files, so it's C++ file. One of them is inputted to the high-level synthesis that will be implemented as a hardware into the FPGA, and the other one is just cross-compiled with GCC and implemented on the CPU. Then we script everything to have the communication with the CPU and the FPGA. We implement the DDR, some I2S, which is the communication for external ADC-DAC, audio ADC-DAC. And we have some control of it. So this is a last file that Faust can generate. The idea is that from your DSP, Faust can generate a graphical user interface that you can run on a host PC. And using a USB cable, you can control your FPGA from your PC. Or you can use a hardware control board. Yeah, and so everything is scripted, is inside the compiler, so you just need to write a Faust DSP, and everything is implemented for you. Even if you change the number of inputs, outputs, all this block will change accordingly too. So the whole toolchain that I show you here, again, it's called Cifara. You can download Cifara on GitHub. It's open source. It's free. Maybe I can show you the Git. Or I will just show you how it's works. So just so you know, if you want to try or toolchain to try everything, you need to install Cifara, which is very, very lightweight. You need to install the Faust compiler, which is pretty light. And the problem is you need to install the FPGA manufacturer tools. So basically the high-level synthesis, Vivado, which is the software that allows you to implement your software onto the FPGA. This is very, very heavy. It's like 150 gigabytes. And the other catch is that everything is running on Linux only for now. So you need Ubuntu. But everything is going pretty fast now. I just did a clean install on this computer a few months ago. If you install the last version of Ubuntu, everything should run very smoothly. Hopefully, it's Linux, but yeah, it's working well. So let's say you install everything. Now you have Cifara installed. We spend a lot of time, especially not me, but Pierre, which is the team engineer, to have a well-documented command line and everything. So you have all the options you can add to the command. I won't go into the detail. So you write your DSP on Faust, and you can choose specific sample rates, some sample widths, how you use the memory. Yeah, a lot of things are configurable. And so let's take our program that I write on my IDE. I just need to take this program. I put it on a text file. It's in my example right here. here. So just to show you that it's exactly the code that I had on my IDE. I didn't add anything. So I put this on a file, and just by writing Cifara and calling this file, and I will not do it right now, but yeah. And yeah, it's compiling, and in 20 minutes, we'll have a working FPGA implementation. About the 20 minutes. So you cannot go really faster than 20 minutes. It's the problem when you program FPGA. If you want to have the whole implementation, it's usually very, very long because the tool needs a lot of time to implement your hardware circuits for the mapping and the hardware implementation. 20 minutes is pretty good. Usually it can take hours or even days. But it's okay. If you have something working, you just have to wait 20 minutes. It's okay. The problem is you don't want to, usually when you program, you just program something and you test it, and you change something, you test it. You don't want to wait 20 minutes each time. So there is, oh, sorry, I forget. Yeah, anyway. There is a solution for that. So if you remember well, we have those 4 resources that can saturate, and if it's saturated, you cannot implement anything. And we have the latency. If you use more than 1 sample time to compute everything, it will not be okay. The thing is, you don't have to wait 20 minutes to have this information. So those 4 bar graphs just give you the resource usage, the percentage. You don't see anything, I suppose. And you can have an approximation in around 1 minute, thanks to the high-level synthesis tool that gives you an approximation. So you still have to wait 1 minute each time you want to change something, but it's better than 20 minutes. It's just an approximation. Depending on the program, it can be pretty wrong, but most of the time is just very pessimistic. So if it's almost fits on the estimation, it will fit on the real implementation. Yeah, just to tell you that we implement some kind of easy programming reports. And again, the idea of this report, that's print, it's this print on your terminal when you finish the command. The idea is that basically you don't need to know what an FPGA is. You just write your program in Faust, and you have those 4 bar graphs, and if one of them is more than 100%, you just have to change your program. Maybe you don't know what an LUT is, you just know that it's 68%, so yeah, you're almost over the saturation point. So yeah, it's very clear. We don't explain anything, we just want to show you that it's fit or not. There is many ways of controlling your DSP. I already talked about it a little bit, but you can either use this graphical user interface that will be automatically generated by Faust when you compile everything. So it's on your computer, and you just have a USB cable to control your FPGA. I just built some modular 8-controller board. And we can implement Linux on the CPU. That doesn't change the resource usage of the FPGA because the CPU is independent. So we made our own embedded Linux implementation. It is still a work in progress, but it's working very well now, sorry. And the idea is that because you have Linux, you have all the Linux peripheral and drivers. And here, as you can see, we use the MIDI over USB to have a MIDI interface. We can use Ethernet, so you can send samples and control over Ethernet. And yeah, you have the whole Linux environment. So you can implement OSC or other protocol that you want. And yeah, this is it for the presentation of Faust to FPGA. So it is working. You can try it. Maybe you have a Faust program and you can see it will fit. The problem is, we take, here in this example, a Faust program, so a very, very simple program, an FIR filter with 250 taps, which is not much. The FPGA costs like 200 euros, so you expect to put more than this very small program on the FPGA. And if you implement it with Faust, you can see that it will use a lot of the resources, so a lot of LUT especially, and it will be very, very quick to execute. If you write the same thing in C++, so just a for loop over the FIR filters coefficient, you will use way, way less resources, and you will be a little bit slower. So there is, again, this is basically the sequential implementation versus the parallel implementation. None of them is better than the other. It depends on your needs. Here, both of them fit in terms of resources and latency, so we can say, okay, it's good like this. But the question is, how do we control this? Maybe you will put a bigger program and the LUT will saturate, but you will have way, way room for latency. So this is at the high-level synthesis level that everything happened. You need to configure the loops, so the for loops or the while loops that you give to the tools, to guide the implementation. I don't have time in this presentation to show you how you guide the tool, but just you use some directive and pragma in your program, or just the way that you write your code will help the tool. So you need the loops. The very, very big problem is that Faust doesn't have any loops inside his code, inside the compiler. This is the way that Faust works. When you write something, it's just flatten everything to optimize everything. So you don't have any loops in the Faust code. So you cannot control everything with Faust. And what is even worse is that the loops allow you to control the trade-off between latency and resource usage, but also the high-level synthesis is very, very efficient to implement pipeline. Again, I don't have to have time to explain how a pipeline works, but it's just very efficient in resource and latency. So if you have a loop, you win in both resource and latency. So in other words, if you don't have loops, as in Faust, you are very inefficient. So this is a problem. That doesn't mean that it doesn't work. Again, maybe your program is light and you can implement it without having anything to do. But if you want to implement more heavy program, you'll need to go deeper into the high-level synthesis configuration. So this was the first step of Cifala, and the next step is to program in C++ to write your program and to give the high-level synthesis tool a lot of information. Both of the approach are available on the tool. Yeah, I don't have time at all to explain you how you optimize your C++ program. This was a huge part of my thesis. If you want to know more about it, I can talk about it later. But again, the idea is to want to use sequential language, C++, to design parallel hardware circuits, which is not made for it. So you need to give a lot and a lot of information to guide the tool. You need to know the trade-off you need between the latency and the resource usage. And a very, very important part is that the high-level synthesis tool will try to optimize your code as a default behavior. The problem is it's not made for audio program. Audio programs are inherently sequential, which is not how the high-level synthesis tool works. It works with, most of the time, video or Ethernet flow, which are completely different. And so the default behavior of the tool, of the optimization, is very, very wrong for audio system. This is why you really need to give the tool a lot of information to just erase the default behavior and have your own configuration. So yeah, during my thesis, I try to give a lot of guideline to help this part. So basically, I give some template on your code and also give you some information. If you write your own C++ code, I have some guidelines that tell you if you use a two nested loop, just write them in a certain way to have a more optimized audio program. Yeah, again, if you're interested by that, we can talk about it later. So we have software that implements Faust code into an FPGA. Now, how do you interface 50 speakers to one FPGA? You have a small chip. At best, you have a development board with one audio codec and a stereo output. How do you implement? How do you connect 50 speakers to this? You'll need to do some PCB, but we'll see that. Just why would we need 50 speakers or more? This is just some example of multi-channel application. So again, this holoplot implementation. Just to give you some numbers, in the Las Vegas sphere, they use something like 1,500 of this block, and each of them embed around 100 speakers. That's a lot of speakers in one room. I don't know if it's useful, but yeah. Or you have some more artistical presentation. So the Ambisonic Dome at IRCAM in Paris, and the WFS system at the ARG. So you need a lot of speakers for this. So we need a lot of speakers. How do we interface them? So first, the analog to digital interface is made with an ADC and a DAC, of course. Something pretty important to notice is that audio ADC and DAC are very specific compared to classical ADC, DAC. So usually classical ADC will work at very, very high sampling rates, but with a very low resolution, like 12 bits. It's not so low, but it's slow for audio. For audio ADC, you want to use at 24 bits usually, and more than 768 kilohertz. Yeah, I don't know if there is application, but usually you are at 48 kilohertz, so you don't need a very, very fast sampling rate. Here you can see one of the ADC DAC that I used, a very, very small square here. And yeah, just so you know, they are usually called audio codec, which has nothing to do with the software codecs, but it's called an audio codec when you have an ADC and a DAC under the same chip. And this is very important because the audio ADC and DAC will bring a lot of latency. The two main sources of latency are the buffering when you use an OS and the ADC-DAC converter. And yeah, to show you an example, in the state-of-the-art, the smallest latency for audio processing was 180 microseconds from analog input to analog output, so the whole system. And using very, very low audio codec, we achieve, for the same sampling rates, 30 microseconds latency from analog input to analog output. And you can go as low as 11 microseconds. Yeah, so yeah, I'll go very quick on this. Just to communicate with an audio codec, you use an I2S protocol, which is the standard for audio communication. And the idea is that you can time division multiplex. So in one wire, you can send up to 16 channels. And for the for the I2S communication, you will need 1 or 2 clock wires and 1 data wires. So it's 3 GPIO, and you can share the clock wire between every audio codec. So in other words, you need 1 new GPIO for every 16 channels. So just to show you, on a very basic evaluation board, you can have 40 GPIO, which is more than 600 channels. And if you do your own board and you have all the GPIO of the FPGA, you can theoretically go to up to 4,000 channels on one chip. The question is, what can you do with 4 channels on one chip? What kind of computational load you can impose to an FPGA with 4,000 channels? But theoretically, you can do this. This is why FPGA are very good. So yeah, you just add more ADC, DAC, and you have more and more inputs and outputs. So yeah, 32 I2S channel for 512 inputs and outputs. Yeah, just a little show of what I did. I developed many boards during my thesis. This one is pretty important. It's called a frugal board, as long as you can call frugal a system with 32 speakers. So it's the small white board that you can see here. It's designed to be possible to build by hand. So as long as you can find a way to print the PCB, everything on it can be in a smaller breakout board from Adafruit. And it's embed 32 amplified outputs. So you can directly connect 32 speakers to it. You can connect it to this green board, which is an FPGA development board that is very well known. It's called a Zibo. And from this, you can build your own WFS system that you can see here that I present at Lyon. We build it for less than 1,000 euros by hand. Yeah, again, you just need to find a way to print this PCB. Everything is, yeah, well explained. The PCB is very easy to print, even if you have your own PCB printer. These are a big track to be easy to print. And yeah. So this is the DIY version. This was the first version of the board. You cannot see it, but there is a huge FPGA below this, and it's embed 16 low latency audio codec. So it was designed for interface with an active acoustic control system at École Centrale de Lyon in Lyon. And so the last board, which is the one I have here, which is like the more finished one. It's embed an FPGA just here, and you have all the interfaces. So you have 32 inputs, 32 outputs, and yeah, the idea is that you can program it directly. It wants to be very straightforward. So you just program your Faust DSP on it. Everything is already interfaced, and you can have your 32 inputs, 32 outputs system, and you can stack them. Probably up to, for now I say 256 channel, but you should be able to go way higher than that. And yeah, this is basically what Polyphonic is, this board. I don't sell anything for now. The production cost is less than 1,000, just to give you an idea of what this kind of system can cost. And yeah, this is what I present today, basically. Just a quick conclusion, what did I present you today? So again, Cifala, it's an open source software. You can download it as long as you can download the Xilinx heavy tools. And you can program an FPGA using the Faust programming language or C++. You can reach latency up to 11 microseconds from analog input to analog outputs. You have lots of multi-channel capabilities, and it's made for allowing you to it's made for a very efficient hardware implementation. So what you can do now, again, download Cifala, download Faust, download Xilinx on a Linux computer, and you can try the toolchain. Everything should run well. Cifala is already used in some other universities, especially Stanford. At Menus, they used to use it, I don't know now, and in Central Lyon. And the idea is that so I developed this board. My fund will be done at the end of the year, and I need application. I'm not an audio engineer. I'm a computer science engineer and researcher. So I don't really know what are the needs. What could be the needs and the application with a low latency multi-channel board. So if you have application in your mind, please come talk to me and we can see if we can do something. Yeah, looking for projects, and yeah. Thank you very much, and if you want to contact me.
Hi.
Hi.
Thanks for the presentation. Before I ask questions, can we just go back on slide 19, please? And can you just tell us what is the scope of your contribution in this massive project?
This one?
Yes. So what was pre-existing in Faust, and which part did you actively develop?
Yeah. So again, the two creator and main developer, only developer probably, of the Faust program and compiler are in our team.
Okay.
That makes things way easier.
Yeah.
So we, you know how the Faust compiler work, if you have discussion or?
No, I know more about the FPGA.
Okay, so Faust work in a way that you can add something called architecture files.
Okay.
And so, for example, you tell Faust that you want to generate C++, it will generate kind of an API, and you can encapsulate everything inside your own file, so
yeah.
calling the right function. This is basically what we are doing here. Faust generates the same file, but we encapsulate everything in our own file that call only the function that we want. And we, so I didn't directly modify the Faust compiler. I asked Jan Orlai.
Sure.
For the one sample approach. So Faust was designed for CPU, so you have the buffer that's only do the computation as buffer. So we just asked him to use a one sample approach, so just erasing any buffering. We changed the memory layouts. Again, the idea is that we just check the size of the VRAM and Faust stop putting a variable in VRAM if it's saturated, and it just declare another structure, and we call this structure as we want. So we have to modify a little bit the Faust compiler, and we have our own option when we call it. That is hidden by the whole framework. Yeah, so we just change a little bit of the Faust compiler, especially for us to be easier to call the function that we want.
Yes, sorry, I just meant, did you work mostly on the UECPP to PC, or did you work on just the PS part? Did you work on the system on chip? Did you develop the PCB? Did you work on the DDR drivers? What was your contribution basically to
so yeah, the PCB it's on mine, and yeah, basically I was for the 2 first years of my thesis, I was alone on this. Okay. So I did the FPGA implementation and CPU implementation. Right. This looked like a lot. Honestly, it's just a
it's
file
a
generator
or something. Okay.
Yeah, but so yeah, audio IP and the CPU and audio codec and PCB.
Okay. So in that case, yes. So how did you manage the float because Faust, I suppose, is floating point numbers, and how did you manage the float to fixed conversion? Using VTIS or mostly for Vivado implementation?
Yeah, you can use float with high-level synthesis.
Okay.
So we just give float, and we have a very, very ugly scale factor to just take the float, and we just multiply it by a huge number to put it in the fixed integrament. We try fixed points at the beginning. So yeah, there is two parts on this. In our team, we have Florent Deninchin, which is a very well-known researcher that works on floating point on arithmetic on FPGA, and we wanted to use his library, so he do some floating point operator. Yeah. It has been a lot of internship, but we never made it work. And yeah, fixed points we try at the beginning. We have some example at work at fixed points, but it's way harder than we thought to have the right. You can have just a huge fixed point and say that everything will fit in it.
Yeah, but then it's DSP costs.
Yeah.
So okay, so you store all your FPGA operations are 32-bit float numbers.
Yeah.
Okay.
And high-level synthesis handle everything. Sometimes very poorly. That's why we want to have a fixed point one day. But yeah, this is way more work that we thought. Yeah.
And yeah, I mean, at some point you also claimed at the end that you have 11 microseconds of latency, but maybe at the sample rates.
768, yeah.
Okay, so it's at the maximum sample rate.
Yeah.
Okay.
That's why I also put the 182
okay.
to be fair.
Okay, I didn't spot that.
Yeah, sorry. Yeah, it's. Yeah, it's at 11. And to be also, yeah, I didn't went much on this point, but because we work at one sample process, if you work at 768, you have way less latency available. So yeah, of course.
And roughly, what's the speed of the system clock that you use in your FPGA? Like, do you run 125, 200, 300 megahertz?
120, so to be exact, 122.88 to have an exact multiplier of 48 kilohertz. But yeah, 125 megahertz.
Right. Okay.
We could go higher, I suppose. So I'm not an FPGA developer. If I go higher, I have a lot of
timing issues.
Yeah, and I'm not sure if it's still working. So, but too much warning for me.
Clicks and things. And what drove the choice of the AIL? Why analog devices for?
So why analog devices? Good question. Seems to be one of the biggest. At the time we used this one, this was the lowest latency. I think it still is. On this board, I changed my approach and I use separate ADC, DAC. And the DAC are the ADAU still, 1966, and it's 16 channel under the same chip.
Okay.
So
Yeah, so you have many channels.
yeah.
Okay.
It's less low latency ', but you can still reach the group delay. The announced group delay is like, I think, 10 microseconds at 192 kilohertz.
And one last question, then I stop. For the DDR, so that's DDR3 that you have on the module. How did you handle the PS2PL communication? Like, did you write a custom driver? Did you just do simple DMA with an AXI bus?
So yeah, it's AXI, a master AXI, and we just save memory addresses.
Yeah.
And so it was at the beginning of my thesis, but if I remember well, the CPU saves some space and send the address, the base address to the FPGA. And
so did you benchmark a little bit how many read and writes you can do at 96K or 48K?
No. So yeah, two things about the DDR. It's very poorly done. We don't even burst. We implement burst at some time.
Okay. That's
yeah, we don't even burst. The thing is, we don't use DDR much because it's supposed to be used for delay line and everything.
Yeah.
And in the end, we didn't find any application when you need very low latency with a delay line. So we kind of stopped this and focus on the BRAM where most of the time everything fits. And what I wanted to say for I forgot, I think. Yeah, it's not CPU and FPGA, there is no, they never write or read at the same time, because when the CPU writes on the DDR, it's only for the initialization. So the CPU writes all the wavetable and everything, and if the FPGA needs, it will read on this. But the control between CPU and FPGA goes through a AXI slave standard.
Yeah. Okay.
So yeah, the DDR it's here, it's working. If you do heavy work on this, it will be very quickly, bad thing will happen. But we try to burst during a time. I think we should, if I found time one day, I will, yeah.
Okay.
But yeah, I know this is a huge problem.
Thank you. Nice presentation. At some point, you mentioned that high language level systems rely on loop structures to generate efficient hardware pipelines. And you also said that Faust flattens all loops.
Yeah.
So that's because it's built with functional language assumptions. Can you speak more about that?
I'm not sure I would be very accurate on Faust. From what I understood, the way Faust can be efficient is that when you write something, it will flatten everything in a way that if you are doing some redundancy in your computation, for example, or if some thing can be done quickly, it will see it. So I think it has something to do with the graph view of the code, but this is where I am totally out of my bounds. What I know is what Jan Orlai always say is that the whole point of Faust is to have no loops, and he don't want loops.
Yeah, it's typical functional language.
Yeah.
So I see that the differences in efficiency mostly lead to resource kind of like inefficiencies in terms of the fabric that's built.
Yeah.
And in C++, you do get the parallelization, right, of the loops.
Faust is parallel because everything is sequential. So everything is written. Every line is written. So the high-level synthesis tool will just say, okay, we parallelize everything. And when it's a loop that is not unrolled, mostly the high-level synthesis tool will try to parallelize. And again, more than parallelizing anything, it's pipeline. So pipelining is just that you reuse the same hardware, but very efficiently. No, I don't have the graph I showed you yesterday. First you want loop just to be efficient. If you don't have loop, you still have this trade-off between latency and resource usage, but it's just not efficient. You have a way of using less latency and less resources if you pipeline, if you have loops. And yeah, I don't think you can add any pipeline if you don't have any loops, or you have to do it by hand in your program, so in the end you know where the loops are.
Thank you.
thank you for the presentation. I just have a problem because have you ever sought connect FPGA to biometric signals, like interaction like EEG or skin conduction? Like they both need really low latency to interact.
Yeah.
Like say, if I want to build a connection between them, how can I achieve it? Or have you ever got some example about it? Thank you.
I'm not sure I get everything, sorry.
Yeah. I mean, have you ever sought to connect FPGA to biometric signals? Like the EEG connection or something like that?
No,
Yeah.
we never tried that. No.
Yeah, but do you think you can achieve that? But like say if I want to build a connection between that, how can I achieve it? What's your idea?
With a biometrical?
Yeah.
It's like a sensor? Or?
Yeah, it's like a sensor. How can I build it?
Well, if you want to connect an external sensor, the easiest way is to go through the CPU because you have most of the communication protocol driver already implemented. It's can be slow. It depends what kind of latency you expect. It can be a little bit slower than going directly to the FPGA. You could implement your driver as a hardware into the FPGA, which is a lot of time and development, but it should work. Or you can go through the CPU, and if you want to send data very quickly to the FPGA, you just implement a DMA. I implement a USB class to have this working as a sound card, and this is what I do. So you just send as fast as possible everything you receive on the CPU to the FPGA, and so the CPU is kind of transparent. Yeah, it still adds some latency, but it depends what you need in terms of latency. I'm sorry, I'm not sure. Do I answer your question? Or?
Yeah, thank you.
Yeah.
Well, first of all, congratulations for explaining in less than 1 hour high-level synthesis, C++, FPGA, lookup tables, hardware and memory resources. It's fantastic, really, really well. It seems that you have done this more than one time.
Yeah.
for your
PhD
thesis.
defense is still fresh.
It's really challenging, so really challenge. Yeah, congrats. Anyways, 2 questions. The first one is like, because in Faust you have a set of archetypes or like modules, right? Like the oscillator modules, you have sinusoidal oscillators, I don't know, like different types of primitives, right? Sound design primitives. Well, did you implement each one of the primitives in using like high-level synthesis?
Yeah, okay, no.
Okay.
This is also a problem going on. Some Faust code will just not work at all. By experience, the more Faust user library, Faust library you use, if they are very complex, the more difficulty you will have. If you want to implement a reverb and you just call a freeverb demo on Faust, I don't really know what will happen because I don't know what happened in the Faust function. If you want to do it by yourself, it's better. But now you can say, yeah, it's the whole point of Faust is using those library. This is one of the problems is that, especially me, so I'm not I don't develop in Faust at all. We have Susi with especially Jan Olay and Stefan Letz that are the creator of Faust, and they are able to tell you if your approach is good or not, which is very, very manually for now. But no, for now, it will depend a lot of what you implement. The sine wave example is a very good one. There is like probably 5 or 10 ways of generating a sine wave on Faust, probably at least half of it will work, but very, very under-efficiently. This is a problem. So we don't know right now if we do like a sub-class of Faust where only the thing that can work very well can be called. Yeah, you have to see. Basically, when we try to implement a new program, we just do the simulation and see if it can fit or not. We have sometimes very, very good results, and sometimes, yeah, it's very bad. So, but for the main one, maybe I have the main application that we implemented. Yeah, so WFS is working well. We now have an ambient sonic decoder of order 4, I think. Yeah, stuff like mixer are working very well. Everything that's called square roots or stuff like that are working very badly. Modal synthesis is working well. And again, the problem is sometimes you just do a small thing that will force some very heavy mathematical function to be implemented on the FPGA, where you could, in fact, do them on the CPU just if you rewrite a little bit your program. So again, if you code in Faust, this is not perfect at all. I cannot guarantee you that it will fit. It's better than if you have to rewrite everything in C++. But this is where you have to try, and sometimes it will be very efficient, sometimes not. For now, we have to work on this.
Mm-hmm. No, fantastic. It's really interesting because, like, the characteristics of the underlying C++ HLS that you have to write HLS, C++ HLS in a specific way in order to make it work in the FPGA, somehow creeped up to Faust.
Yeah.
And now you need to write Faust in a very specific way. So it's super interesting, right?
Exactly.
That crystallizes. And my last question is, if you go back to the resource table that you had, like the HLS comparison with higher latency, but with the pipelines, right?
This one?
Yes, that one. It's like my question there is like, okay, yeah, it's an FIR filter. Okay, yeah.
Yeah, it's just a multiply and accumulate function and a shifting buffer. So just 2 for loops. Okay. I can show you the code if you want. It's a very, very simple one. Just 2 for loops, and yeah, Faust just write everything line by line. Mm-hmm. Which for the high-level synthesis tool means, so yeah, this is also a very specific stuff from Xilinx, so the manufacturer of the high-level synthesis tool. The tool is very, very hard to predict, especially the default behavior, depending on the version you use. Sometime if it's a loop with more than 10 iterations, it will be sequential, and the next version is the opposite, thanks to Xilinx on this. It's tend to be better now. They just do something.
That's why all FPGA developers are obsessed with specific versions of Vivado and specific versions of HLS. Yeah, I know it very well.
Yeah.
Okay, fantastic. Really good work.
So basically, if now, let's say we have one FIR with 250 taps, but if I get 16 FIR filters still with 250 taps, mm-hmm. will the Faust approach just increase? Will it just increase the BRAM utilization and while keeping the same amount of DSPs, or will it scale it in that direction, or with pragmas or?
For the Faust approach, so it will be the dummy approach. Okay. I think it will just scale everything up 16 times.
Okay, so sorry. So the purpose of this was to show that writing your own C++ will always end up being more efficient than Faust.
Yeah. Okay. So efficient, or at least you have control. So this is exactly the point. If you write a 16 FIR filter, maybe you will just have 16 times more latency in C++. So then you will see your code and say, okay, I don't want to sequentialize my 16. Okay. And this is where I provide guidelines to explain you how. If you want to increase resources or latency, how do you add this 16 loop, for example? Right. Yeah.
Hi. Thanks. Very interesting talk. I was thinking about your last slide, and you were talking about applications. My question is very similar to whoever that person about the heart monitoring earlier on. Is can you take complex signals and run the system in reverse? Taking a complex signal, breaking it down in real time, and then using what you generate there in terms of multiple signals in real time?
No idea.
No. I'm just thinking about things like, for health monitoring, for in medtech applications, or process control, or monitoring of equipment, asset integrity live. Yeah, things like that. So you break things down into its component signals. And in real time.
In real time, yeah. Well, if it fits on our system, it's in real time. But this is the only guarantee I have. I won't answer anything. I don't know. Yeah, sorry. but
everything that you're doing, but in reverse.
yeah. I see the idea, but I suppose you could. We could try this. But yeah, right now we didn't try this at all. Yeah, it should be possible. I think you have to write everything in C++, definitely, not in Faust. But yeah, should be possible, yeah. Sorry, I don't give you more information.
No, but it's maybe you're asking for applications. It's something you can
Yeah, this is interesting. I will check about it, yeah.
Yeah, actually, if I could just follow up on that, I think it's a really interesting application. And it's not so much maybe something for Faust specifically, but for the Polyphonic board that was presented at the end. I mean, I noticed that in your examples, you focus on all of the audio outputs, right? Lots and lots of speakers, wave-field synthesis and such. But you equally have as many inputs, and there are lots of different applications, not only in sound and music, but in other kinds of signal processing domains, where tons and tons of inputs processed in real time, in parallel, feature extraction, what have you, would actually be extremely useful. And so, I mean, I guess, you know, it seems to me that what you're doing at a hardware level, and, you know, potentially at a sort of synthesis level, could support that. And I think it's actually a really good suggestion to be looking into other domains where those kind of signal inputs could be used.
Yeah.
Yeah, this is super interesting, and I kind of follow up on that, and maybe a specific question around this, for doing some like signal processing and like applications in, say, like neural audio synthesis, or doing some like inference with neural networks, something that like it seems like doing matrix operations would actually be well suited for the FPGA, if I understand correctly.
Yeah.
And what would the limitations in terms of, say, like storing model weights, and if you have, how big of matrices can you have, and
yeah, this is kind of a question that Andrew asked me during my test and that I wasn't able to answer. And I'm still not really able to answer that. So I don't know much thing about a neural network, and so I have no idea how the weights.
If you, I guess at a basic level, just doing like a matrix multiplication.
Yeah.
And if you have a predefined matrix, could you store that on the FPGA, or where would that maybe live?
Yeah, you can store this. There is many work on FPGA for a neural network. So yeah, if you have a predefined matrix, you can store it on the VRAM of the FPGA for sure. But for the size, yeah, I cannot give you any order of magnitude. But there is for sure a lot of work going on FPGA. On this, yeah, and I know one guy from the team tried to implement this in Faust, so using Faust to implement a neural DSP, but yeah. Yeah, I'm sorry, I'm out of
a bit into that actually. And so the main limitation that you're going to have is the size of your data. So first, if you start with floating point numbers, that will eat up all your internal RAM. Because like, for example, if you take the board Genesis, so the big one, the Zinc Ultrascales, you will have something like around 7.6 megabits available in the FPGA. So that's not a lot to store your weights. So the way out of that is either to use a fixed point for your weights and have a small format like 1.16 or something like that. So the more you reduce your weights, the more you will be able to have in real time. And then if you start using ultrascales as well, you can also leverage the CPU and the external DDR, and then you have your workflow with ONNX, etc. So you can use that in floating points. Or use the internal GPU of the ARM processors, the Mali CPUs, where you can have SIMDs operations that happen there. But then you lose a little bit in the loading those in and out, and then you lose a bit in real-time operation. So that's things you can try on FPGAs and leverage both. One more question.
Yeah.
Did someone do some spectral implementation for the FPGA? So, or is everything implemented so far just time domain?
Yeah. So first, Faust doesn't like FFT very much.
Okay.
There is some FFT function that are implemented. I know one intern worked on this very recently.
Yeah.
Yeah, I was already defending my thesis, so I didn't follow up very much.
Okay.
For now, it's way easier if you are in the time domain. The few applications we have, I had some binaural core that I implemented.
Yes.
We try at the beginning to stay in the frequency domain and then just put everything in time domain, which is way easier for now. Yeah, it's also a work in progress because it's also a kind of problem. Many people ask me if
I suppose.
Yeah.
Okay.
But yeah.
Great. Well, thank you very much. Great
Thank
talk
you.
and great discussion. And yeah, we can continue it after this. Right.
Great.
Thanks, everyone.
Thank you very much.